Assalamualaikum and welcome to the video. In this video we are going to look at chapter 4, basic forces and free body diagram. If you look at in the slide, we have the equation of impulse. So F times delta T equals to delta P. F is the force that is applied to an object, and delta T is how long the force is applied or how long the force is in contact with the object. And the product of force times the time of impact is equals to the change of momentum of the object. So change of momentum of the object is just the final momentum of the object minus the initial momentum of the object. In chapter 3, we only consider one forces that is acting and changing the momentum of the object. What if we have more than one? So we are going to answer that question later in the video. But before that, I'm going to introduce to you the forces that we are going to study in this chapter. The first one is the force of gravity. The symbol is W. W stands for the weight of the object. The second one is force in a string. So force in the string, we call that force as tension, and the symbol used is capital T. The third one is force exerted by any surface to an object. So when that object is sitting on the surface, so the surface or the plane is applying a reaction force to the weight of the object. So the F reaction is called the normal force. The symbol used is N. So force of resistance to the motion of an object is called the friction. And we have two types of friction. So the first one is the static friction. Fs stands for static friction. This is where the object is stationary, and static friction is always bigger than the kinetic friction. The equation for static friction is mu s times the normal force on the object. Alright, and the equation for Fk is mu k times n. Because Fs is always bigger than Fk, so Fk is the friction for a moving object. So means that the object is already moving. Alright, so the friction change from static to kinetic friction, and the value of static friction is much bigger than the kinetic friction. Means that mu of s is going to be always bigger than mu of k. Alright, so finally we have the fifth one, which is the external force. So any force that is applied to the object, and the symbol used is just F. Alright, so far we have 5 forces. The first one is the weight W, and then we have tension, and then we have normal, and then we have friction. We have two types of friction, so Fk and Fs. So one is kinetic, moving object. Fs is static, for stationary object. And then finally we have external force. So this is all the force that we are going to study. Now I'm going to take you to a simulation on how to draw the W, the N, the F, and this one, the external force. Okay, I'm going to use this simulation to introduce to you how we draw the forces on an object. Alright, so what we have here is a crate on the floor. And if I take the force vectors, we can see we have two vectors that is acting on the crate. The yellow vector and the blue. The blue is Fg. Fg is a force of gravity, force exerted by gravity. So this is actually the weight of the crate. So because the crate exert a force of gravity on the floor will exert the same amount of force, but in the opposite direction. So the force is called the reaction force or the normal force. So it is labeled as Fn. So Fn is the reaction force or the normal force exerted by the floor on the crate. So we are drawing all the forces acting on the crate. The mass of the crate is 100 kilogram, as you can see here. If you can see from the simulation, the way we draw the Fg and Fn. So Fg is pointing straight downwards, so that's how gravity is acting on an object. and Fn is drawn perpendicular to the surface of the floor. Alright, it's perpendicular to the floor at a 90° to the floor. So I want you to watch closely what happened if I raise the floor up. Alright, now I raise it up, so maybe up to here. So if we again look at the force of gravity, it is still pointing in the same direction. It's still going straight down. Okay, so but what happened to the force of to the reaction force is that it stays at an angle of 90° to the floor. So that is how you draw the gravitational force and the normal force to an object. All right, so normal force is always at an angle of 90° to the surface, and force of gravity is always downwards. So now if you can see from the simulation, we have another forces, the red arrow there. It is labeled as F of small f, so that is basically the frictional force. So we have three forces there. Because now the floor is raised up, the crate has a tendency to slide down. So the way the friction works is it is always trying to oppose the motion. That is why the direction of the frictional force is that way, because the crate is trying to slide down, so frictional force will try to oppose the motion of the object. So that is how you draw weight, normal and frictional force. Alright, now I have raised the floor a little bit higher, and we are going to apply an external force pushing the crate upwards. So I'm going to use the wooden stickman to push the crate. So I'm pushing the crate, that way, so upwards. So as you can see, now the friction is acting on the opposite direction to the direction that I'm pushing the crate. So as you can see, we have another forces appear there, Fa. So Fa stands for an applied force or an external force. So because we're pushing it up, that is why Fa is pointing up the ramp. And then the frictional force suddenly changes direction. Now the frictional force is acting against the Fa. So if we remove the Fa, the force is going is acting that way. All right, so that is how frictional force works. It always opposes the motion of the object. All right, that is all I think for this simulation. We'll go back to the slide. Thank you very much. Okay, coming back to the question that I've asked earlier in the video. What happens if we have more than one forces? The answer is we have to find the sum of all the forces. The sum of all the forces, the net force, times how long the force is applied, is going to be equals to the change of momentum of the object. So this equation, we can rearrange the equation. We'll get F net, okay, the magnitude, just the magnitude. We remove the arrow sign there. So is equals to the change in momentum over change in time. So this equation is telling us the rate change of momentum, how much the momentum change every second. So we have the final momentum. The final momentum is mv, initial momentum is mu. So that is the change in momentum divided by how long the change happened. So equals to, we can take out m. So we have v minus u divided by delta t. So this gives us the equation of ma. So net force acting on an object, so the net force acting on an object can be calculated from the mass of the object times the acceleration of the object. So for our syllabus, we will be only dealing with 2D forces. Means that you need to do resolving vector. You are going to resolve the forces into x and y component, and then we are going to treat them separately. So in the x component, if the force are in equilibrium or the force is balanced, means that when you add all the forces in x, it's going to add up to 0. So means that the acceleration in the x axis is 0. So the implication is you have no acceleration in the x-axis, no change in the velocity in the x-axis, and because the force is 0, so there is no change in the momentum in the x-axis. Same goes for the y component. So when you resolve the vector and then you add the vector by its component, and when you add the vector force in the y direction and you get 0, means that the acceleration in the y also 0. Alright, there is no acceleration in the y-axis. Imbalanced force implies that when you add all the forces in x, if it is not 0, the magnitude of the force is going to be equals to the mass of the object times the acceleration of the object. Alright, so in this case you have imbalanced force. Same goes for y-axis. If the sum of the force in the y is not 0, so it means that the magnitude is going to be equal to the mass of the object times the acceleration in the y. So this is the acceleration in the x. Okay, so remember, in 2D forces we are going to treat the force separately by its component. So we are going to continue with an example. So let's go to the next slide. Okay, in this slide we have a block on a floor, and it says here the floor is frictionless, so we do not have to consider the friction between the block and the floor. And it says here you need to calculate the magnitude of the normal force and the acceleration of the object. So let's say the acceleration of the object is in the x component. So this is the acceleration of the object, and we do not know what is the value of the acceleration. So if you look at from the acceleration, you have the acceleration in the x. So straight away from the question we can write that the sum of the force in x is going to be equals to mass times acceleration, because we don't have any acceleration in the y, so the net force in y is equals to 0. So this is the first condition that we have to establish. And then I'm going to clear this out because I need to draw the vector weight and the vector normal. Okay, now it is given to us that the external force is applied at this angle 45 degree, because when we draw the forces on the Cartesian, we need to place the tail of the vector here at the origin, so we need to know what is the angle here. So because this is 45, so means that this angle is also 45 degree. Okay, then we need to draw the weight. So the way we draw the weight is always acting straight down, so this is the weight, and the normal is always perpendicular to the plane, so this is the normal. So the weight can be calculated using the equation m times g. So we have 1.02 times 9.81, so this will give us 10 Newton. So I'm going to go to PHET and use its simulation to try to solve this problem. Let's go there. Okay, now I have included the vector A. So vector A is actually the force, because I cannot change the convention that PHET used for the vector. So we are going to assume A as the external force with a magnitude of 11.3 Newton, and then the angle from here to the vector force is 45 degree, but in the simulation it gave us this angle, so 135 means that this angle is 45 degree, and then this is the weight. This method is known as the free body diagram. So free body means we exclude the body and we only represent the body by a single point here. So and then we can draw a Cartesian to help us to visualize the vector better. Alright, so we are going to place our tail of the vector at the origin of the Cartesian, or the origin of our free body diagram, the point there. So the point is going to represent the object. So we have the vector force with a magnitude of 11.3, and the direction is 45 degree below the negative x-axis. So just by looking at the vector force, we know that we have to resolve the vector force. So if we resolve the vector force, we'll get that the horizontal component of the vector force is 8 Newton. The vertical component of the vector force is also 8 Newton. Okay, so we have resolved the vector force. Now we are going to add our vector for the weight. So weight is 10 Newton. Because weight is one-dimensional, so we do not have to resolve the weight. Okay, that is the vector force and the vector weight. And if we click on the sum, it will calculate automatically for us the resultant vector for weight and the force. If you look at the resultant vector has a magnitude of 80 Newton in the negative y-axis. Alright, from the equation that we have established earlier, we know that the force in the y-axis is balanced, means that normal force is going to be the force that cancel out the negative 18, so means that the magnitude of normal is positive 80 Newton. So now resultant is showing us that it's only have a horizontal component, so the resultant force is 8 Newton pointing in the negative x direction. Alright, we are going to prove that this is actually the solution for the questions. So going back to the slide. So if you look at the solution from the simulation, this is actually the resultant force. So this is the resultant force in the x-axis. So we know that because the acceleration is in the x-axis, means that the force are imbalanced in the x-axis. So the sum of all the forces in x-axis it should be equals to mass times acceleration. And from the simulation here, we know that the sum is equals to 8 equals to mass. The mass of the object is 1.02 times the acceleration. So the acceleration is equals to 7.84 ms negative 2. Alright, and then this is actually the normal. So this is the weight and this is the external force. And then for the normal, we know that the sum of force in y should be equals to 0. So when we only add the force with the weight, the resultant force that we get is something like this. We have a resultant force like that, and then it has negative 8 on the horizontal, and if I'm not mistaken, we have negative 18 on the vertical. Alright, so the vector n should cancel out the 18 because the sum of force in y has to be equals to 0, means that n should be equals to 18 Newton, positive 18 Newton, because this value is going to cancel out the vertical component of the resultant, so that we only have resultant in the x-axis as shown here, this one. So we solve the questions graphically, we draw it and then use the simulation to help us. Now I'm going to show you how we can solve the problem manually. Alright, we are going to use table. Okay, first we are going to draw the free body diagram. So we are going to exclude the body and represent the body with a single dot, and maybe add a Cartesian to help us to visualize the vector. So we have x component there, and then we can add our y component up here. Okay, so we can draw the vector force. I'm going to use the black color pen, and then we have vector force here, and then the magnitude of the force is equals to 11.3 Newton, and this angle is 45 degree, and then we have width equals to 10 Newton. I'm not going to calculate it again. And then we have normal, and we do not know what is the magnitude of the normal force. So we have three forces here, so I'm using table so that it is easier to see the force in separate components. Alright, so the first force we have is N, and then we have W, and then we have the force, external force. So because N is one-dimensional, so the X component of N is 0, the Y component of N is positive N, because it is pointing upwards. So the W, the X component is 0, the Y component is negative 10. Alright, and then for the force, we have resolved it. We have resolved the force, but I'm going to do it again. So resolving the force is we want to find the horizontal vector and the vertical vector of the force. So if we are using cos 45, it's going to be equals to, this one is fx and this one is fy. So cos of 45 is fx over 11.3, so you get fx equals to 8 Newton. And then if we're using sine 45, equals to fy over 11.3, so fy is also equals to 8 Newton. Okay, one thing I forgot to mention here is that we are going to take the direction of acceleration as a positive direction, as I've written here. So because of the acceleration is pointing to the left, so we are going to take the left as positive and the right as negative direction. So fx here is going to be positive 8. So instead of negative, we are going to have a positive 8. Okay, remember we take the direction of acceleration as positive direction. So and then the direction of y, so as usual downwards direction is negative 8. Okay, and if we add up all the x component, we should get the value must be equals to the mass times acceleration. And for the y component, because the force is balanced, is going to add up to 0. So from the table, we know that 0 plus 0 plus 8 is equals to 8, and the mass is 1.02 times the acceleration. So the acceleration is positive 7.84 ms negative 2. Okay, and for the y component, so we have n plus with negative 10, so n minus 10, plus with negative 8, so minus 8, and this value is going to add up to 0, so n is going to be equals to positive 80 Newton. So the same exact answer that we get with the PhET simulation before. So in here, so we have the magnitude of the force, so the direction of the acceleration, so we take this direction as positive direction, because acceleration is pointing in the same direction. Alright, so we take it as positive, so we get a positive value for the acceleration. Alright, I think that is it for the video. We are going to discuss more examples on the chapter using the model module. So I hope you complete all the chapter 4 example in the model module, and see you in the Google Meet session. Thank you very much.